All right, I'll stop at 40. Well, let's look here. So a kilowatt, actually, we'll just say watt times seconds because a kilowatt is a measure of power, hour is a measure of time. So I'll just break it to our SI units, which are watts and seconds. And a watt has basic units of what? It's energy per time. Energy is measured in what? Joules, right. So I'm going to have joules per second times seconds. Notice that our time cancels out, and I'm just left with joules. So you're paying for kilowatt hours, which is a measure of what? Energy, right. So, um, energy doesn't really care the amount of time that you consume the electricity in. They just care about the total amount of electricity that you consume. So they're not concerned with the power consumption, but rather their energy consumption. Um, well, we often get those sort of mixed up in our head. And what contributes more to the cost of your electric bill, a 1500-watt hairdryer or a 600-watt microwave oven? Hairdryer, oven, equally depends upon what you cook, or depends how long each one is on. All right, I'll stop at 35. 35. All right, E is the right answer. Remember, Entergy is concerned about your energy consumption, not your power consumption. So it doesn't matter that this is 1500 watts and this is 600 watts. It really depends how long you use either one of these. Uh, and, I use a hair dryer for like 20 minutes every morning. That consumes a lot of power. I don't use a hair dryer at all. But uh, but if you do use a hair dryer, it sucks a lot of energy. It's like one of your most energy consuming devices in your whole house, apart from like your clothes dryer and your dishwasher and stuff. A lot of energy. We'll talk about that more next semester. Have y'all ever put a light bulb into a microwave? You should try it. Look it up on YouTube and then go home and do it. You have to put it in water, but it's really cool. We'll do it next semester when we do electromagnetic radiation. But try it out. It's really far out. It's pretty cool. What's that? No, look it up. It's on YouTube, but you can do it at home too. It's a lot cooler when you do it yourself. All right. Okay. Sort of ho hum on that, but it's Monday and it's 7:30, so I know it's hard to get kick started. But I'll tell you a joke anyway. You want to hear? Yeah. What happens when a frog's car breaks down? It gets towed away. Okay. Um, Make sure you're up on that. I don't think that chapter is too terribly difficult, but you will see, well, there are some difficult things in it. You'll see some variable forces where you have to integrate over the force to figure out the work that's being done. You'll see conservation of energy, like a bead on a track kind of thing. I might even throw in some frictional forces like we did last time where it's on an incline and you have to find how much energy is lost and how high it goes. Or I might even throw in like a variable force. We worked in a problem where you had a variable force on a horizontal plane, but I could throw in a variable force on an inclined plane too. Just make sure that you're comfortable with all those various pieces that we worked through. You will see a dot product. It might be part of a bigger problem, or it might just be here is a force and a displacement. Tell me what is the work that's done by it. Just make sure that you can do a dot product as well. Um, I think that's it for that chapter. Those are all the big topics, work and energy. Make sure that you know elastic potential energy. Could see a conservation of energy problem like we had with elastic potential energy. Make sure you understand the whole positive, negative work thing, what that means. Conservative versus non-conservative forces. I think y'all have that down pretty well. You could see some conceptual questions about that. You'll see gravitational potential energy, elastic potential energy, sort of, yeah. All right, let's move on to chapter 6. Just sort of a quick little summary of what we see in chapter 6, because we're not going to see that much. You're going to see the idea of momentum. Or you're going to see all this again. I just want to give you a quick 2-minute summary. You're going to see momentum. Momentum is the product of the mass and the velocity. It is a vector quantity, so whenever we're dealing with momentum, we'll have to consider it as a vector quantity and deal with its x and y components. Although don't worry, it's nothing near as complicated as what we saw in chapter 4 when we were dealing with forces in 2 dimensions. The momentum is is a little bit simpler. Um, so we'll talk about momentum. We'll see impulse, which is really just a rewriting, or the concept of impulse, which is a rewriting of Newton's second law. That is that force is equal to dp dt, or change in momentum over change in time, or force is equal to the mass times the change in the speed over the change in time. Uh, and so because of this relationship, which is really just Newton's second law, notice mass delta v over delta t is acceleration. In fact, this is how Newton wrote the second law when he first wrote it. Because of this, we can determine forces in collisions really easily. We don't forces are pretty difficult to measure. You have to have some kind of special instrument to measure them and what have you, but it's very easy to measure changes in velocity. Uh, Quite simple actually to measure changes in velocity. And so if we know how an object changes its velocity in a certain amount of time, then we can tell a lot about the forces that were acting on that object. That comes about from Newton's second law, but we'll look at it in terms of momentum. And then we'll also see the idea of conservation of momentum. That is that the initial momentum equals the final momentum. And this will become important when we have objects that are colliding. They'll have initially a certain amount of momentum, and then afterwards, after they collide, they'll still have that same amount of momentum. Finally, we'll look at some different types of collisions as well, not only where momentum is conserved, but also where energy is conserved. So EI is equal to EF, and we'll look at those. You might see those in PChem again, or you might have seen them in chemistry already, because they use them. These types of collisions are called elastic collisions, where both energy and momentum are conserved, and you can predict how gases are going to act because they have both momentum and energy are conserved. And that's it for this chapter. But I'll go over it more here. But that's sort of the summary. We're going to define momentum. We'll look at impulse. Then we'll look at the conservation of momentum. And we'll look at several different types of collisions, elastic and inelastic, where both energy and momentum are conserved. Linear momentum is just a measure of an object's mass and velocity. We're going to call it a lowercase p as the variable we use. It's the mass times the velocity. The SI unit for momentum is nothing fancy. It's just kilogram meters per second. I don't know why there's not a unit. Maybe you can try to make up one and propose it, a unit for momentum. Momentum is a vector quantity. All right, so that's going to mean something about how we deal with it. Imagine that if I have two objects that are moving, so say I have this object, it has a certain mass and a certain velocity, and then I have another object that's moving, it has the same mass and the same velocity. What would happen if I added up the momentum of these two particles? What would it be? Would it be positive, negative, or zero? It'd be zero because it's a vector quantity, right? So both of these would have a certain amount of momentum. This one would have a momentum p. This one would have a momentum negative p because it's in the opposite direction. And then the sum of those momenta, I guess, is would be equal to zero because it's a vector quantity. And we didn't have that with energy because remember, energy is not a vector quantity. Energy is what type of quantity? It's a scalar quantity. So if I have zero energy, what does that tell me about the objects? If I have a system with zero energy, what means? They're not moving at all. So that's not true necessarily with momentum. It could be true. Like if I have two objects that are not moving, I have a mass here and a mass here, and both of them have zero velocity. The sum of these momenta is also equal to zero. but you can't really tell unless you know something about their velocity. Let's try this little quick test. A collection of particles has a total kinetic energy of 0. What can we say about the momentum of the system? Momentum is positive, negative, 0, positive or negative, but not 0. Actually, D doesn't really make any sense. We'll just leave it off. All right, I'm going to go with 45 seconds, 45. Okay, good. C is the right answer. The momentum is 0 because if the kinetic energy is 0, because this is a scalar quantity, because it's 0, the particles are not moving at all. Notice, however, that if instead I said that the momentum was 0, and I asked you about the kinetic energy, what could you tell me about the kinetic energy if I said the momentum was 0? Could you tell me, would the kinetic energy be positive, or would it be 0 or non-zero, or could you not tell at all? Right, you can't tell, because if I tell you the momentum is 0, it might be that the particles are not moving, or it might be that they're moving in opposite directions so that the net momentum is 0. We'll see some more little questions like that later. Oh, sorry. Um, so remember, Newton's second law was F equals ma. But I can also say that this is F equals m dv dt, right? Uh, and based on our definition of momentum, I'll call this dp, is equal to m dv, mass times my change in velocity, or my mass times my velocity. Um, so I can reframe this and say that the force is equal to dp dt. Let's see, get my vectors right. These are all vectors here. Also, I'll just sort of write this as a little cloud. This will come up later. But not only is dp equal to mdv, actually a better way to write this might be to say that dp is equal to dmv. Because not only can it be that the speed changes or the velocity changes, but also if the mass changes. And sometimes we'll see that. We haven't really seen that up till now, but we will see some problems where we have not the speed changing, but the mass changing. Uh, like, for example, like one case that we'll see is if I have a cart that's moving along at a constant speed and I drop masses into it, I change its momentum, and it's going to be like a force is acting upon it. All right, so if I drop mass into it, it's going to cause it to slow down, and that's because a force is acting upon it. So our momentum can change not only because the velocity changes, but also if the mass changes, that changes the momentum as well. Um, we'll define the impulse as the change in momentum. So I, which is the impulse, is equal to our change in momentum. This is just a definition. So I'll write 3 little lines. I is defined as the change in momentum. I'm not going to really use that term. I'm just throwing it out because some people use that term and you might see it in textbooks or whatever it is, other teachers or whatever. You might see impulse. Um, but if I define impulse as the change in momentum, that tells me that I is equal to F times delta T. That just comes about from this Newton's second law, which is that F is equal to delta P over delta T. You'll follow where this comes from? Like if I take this, I can say that delta P is F delta T. And so here I can combine these two. They're both equal to the impulse. I don't know why people do that, but some physicists will talk about this impulse. It comes about because it's nice when you're plotting things, but we won't get into it here. All right, we'll look at some collisions. where we use this in order to determine the forces that were involved. Let's see, the Ford truck. Oh, when I was a kid, like I grew up in the city or out in the country, do you remember? Out in the country, and we had this old truck. It was a '64 fleet side Ford pickup truck, long wheelbase, which wasn't real common back then. Like the '64 Ford truck, they were mostly short wheelbase, and a lot of them were step side too. But this was a fleet side, smooth on the side, and it was a long wheelbase. It was a sweet truck. It was nice. But towards the end of its life, it it just sort of, things started breaking on it, and we didn't fix it. But we still used it around the house. And one time the brakes went out. Right, the brakes went out, and what are you gonna do, right? Well, we would drive it still, even though it didn't have any brakes. But we would just sort of shift it down, so it would slow down, go from third to second to first until it would go as slow as it could. And then what would we do? We'd hit something, right? We had this great big oak tree in our front yard, and that's where we parked it because whenever that's where we'd stop, and we'd run into the tree. And it didn't hurt the truck, right? Because it had this big steel bumper. But we can figure out the forces that are involved just by knowing our change in our speeds, right? So if I imagine this truck, say it's going along at a speed of, I don't know, 1 meter per second, and it has a mass of 1,000 kilograms or whatever, I don't know what it was exactly, and that was its initial speed and its final speed. Let's just say it goes to 0. Then I can find the force. Our force is going to be delta P over delta T, right? My delta P is just going to be the mass times my change in velocity. That's 0 minus 1 divided by delta T. And delta T is the time for the collision. So every collision happens in a finite amount of time, a certain amount of time. And so you just have to estimate this. So you measure the amount of time. It's a small amount of time. Let's just say, I don't know, 0.1 seconds. So that's 1,000 times -1 over zero point 0.1, or negative 10,000 newtons. So, a person weighs almost 1,000 newtons, so it takes about, to stop this truck going at a very slow speed, about 10 times the weight of a person. Uh, so you'll see problems like that. Let's work through another one here where I have a car. It's traveling uh, initially at 10 meters per second to the left. It has a mass of 1,000 kilograms. It hits the wall and rebounds back at 2 meters per second to the right. As you're reading through these problems, think a lot about the direction. You'll see that in your homework. You have a couple of these impulse problems where you have to figure out the forces involved. Make sure you think carefully about the directions and what signs to attribute to the directions. I've already done it here, but my speed or my velocity is 10 meters per second. And notice I've given it a negative. You also want to be careful with your subscripts. I'll put an I on that. So my initial velocity is negative 10 meters per second. My final velocity is plus 2 meters per second. This lady bounces off the wall a little bit. Uh, says that the mass is 1,000 kilograms, and the time that it occurs in is zero point 0.1 seconds. So if I want to find the force that's involved here, my force is m delta v, my mass is constant here, over delta t. That's m vf minus vi over delta t. It's 1,000. Be careful with your signs here. It's 2 minus negative 10 divided by zero point 0.1 seconds. So that's 12,000 over zero point 0.1. It's 120,000 newtons. Yeah, just be careful, especially if you have a rebound. Remember that one of your negatives is going to go away likely, or you'll have a negative here and a negative here, and they'll add up. If you have a rebound, those speeds are gonna add up. All right. Um, by the way, what would happen to the force with the force if it did not rebound off the wall? What would happen to the force if it didn't rebound? It just hit the wall and stopped. What would happen? Would it go up or down, the force? It would go down, right? That's sort of the physics behind. You ever do rat tails? Like, I know the women haven't ever done this, but guys do this. I went to a boarding school in high school, and we would often use rat tails. You know what a rat tail is, y'all? We take a towel, slightly damp is best, and you roll it up. Have y'all done this? Yeah, yeah, but you gotta, right. Guys do it. I don't know why that is, but women don't. Y'all don't do that, do you? Okay. But anyway, you roll it up, and then to really get it good, you have to sort of flick it like this, right? And it hurts if you do it really well. It hurts a lot, actually. Um, but you have to flick it, and the reason that you flick it is what? 'Cause you really want that what? The rebound velocity, right? You don't want this to be zero because if it's zero, then that just takes away from your force. So the rebound velocity, you flick that rat tail because it gives you a bigger rebound velocity. And the faster you pull it away, the more it's going to hurt. All right. So anyway, that rebound velocity is pretty important for the force. Let's see, we can do another little thing here. I have a video I'll show you. They use this a lot in like reconstructing crashes and what have you because, like I said, it's very difficult to measure forces, but it's very easy to measure changes in velocity. So here I have a video. This is from the Honda crash test facility, but they're actually testing dummies, pedestrian dummies, people that are hit by cars. Uh, so in this clip, they set up a dummy, not a real person, a dummy that gets hit by a car. So, and then they talk about the forces that they measure. Now they actually have sensors, but you can do sort of rough back of the envelope type calculations where you figure out the forces that are involved, and we'll do that. If you've ever been hit by a car, I'm sorry, this might be a little traumatic for you. It's not graphic or anything, but if you want to leave, that's fine. I'm serious, like if you've been hit by a car, I think this would be difficult. All right, so we'll work through another one of these, but it's similar to what we did before. Here, though, we need to make some assumptions. First of all, we know, let's just say that our mass is, I don't know, we'll just make it 100 kilograms, so kind of a big guy. Um, and we need to know the initial and the final velocities of this guy. Now, initially, he's stationary, right? So we have zeros meters per second. What was the final velocity of the dummy, you think? Well, but we know how fast the car was going, right? And so I think it was 40 kilometers an hour. And so the dummy's going to reach that speed pretty quickly. So the final velocity is going to be about 40 kilometers per hour. I think that's about 30 miles per hour. But let's convert this to meters per second. So I have in 1 kilometer, 1,000 meters, in 1 hour, 3,600 seconds. You got that, please? 11, 11. Okay, we'll just call it 11 meters per second. All right, so that's our final velocity. We need to make some estimate of the time. Uh, Gosh, maybe 30 milliseconds. That's how long he said it takes the dummy to fall. So maybe it's an estimate, but let's just say 30 milliseconds. So that's 30 times 10 to the minus 3 seconds. That's probably not terribly far off. It might be less. Uh, and also remember here, we're talking about a very simple collision between two bodies, but actually the collision is a bit more complicated because the dummy moves around and not every part of the dummy reaches that speed at the same time. So it's a bit more complicated, but that's what the engineers do. So I can take all this and I can figure out what is my force. It's going to be my mass times my change in velocity over my change in time. So that's going to be 100. It's the mass of the dummy times my change in velocity, which is 11 minus 0, divided by 0.03 seconds. Got that? Is it 0.003? Oh, 0.03 is right. Um, what is that force? Wait, no. I'll just call it 40,000. So 40,000 newtons in order to go from 0 meters per second to 11 meters per second in 30 milliseconds. All right. You could see a problem like that on your test. They're all basically like this. You just have to know the initial and final velocity, and then and know the time interval to find the force. There are some in your homework. Let's try this one, and we'll wrap it up. I think we'll probably wrap it up with this. Let's see what's next. There's an easy way and a hard way to work this. You can try both if you like. All right, I'll stop at 215. 215. Okay, let's see. Let me put A. I don't think A is right. So I'll do it the hard way first. I can find the force is delta P over delta T. Uh, that's going to be our mass times our change in velocity over our time interval. That's going to be 0.5 kilograms times our change in velocity. It's initially going at positive 10 meters per second, and then he brings it to rest. So my change in velocity is just 10 meters per second divided by delta t, which is 0.04 seconds. That's 5 over 0.04. What is that? 125 newtons. So that means that he acts with a force of 125 newtons. And then I know from Newton's second law, F equals ma. A is equal to F over m. It's 125 over the mass, which was zero point 0.5. And 125 over 0.5 is 250. So that is the answer. But look, the real easy way to do this, I know we're about to go, but the real easy way is just to say A is delta V over delta T. Right, it becomes simple then. It's just 10 meters per second over 0.04, and that's also equal to 250. All right, folks. See you on Wednesday. Don't forget our assessment will be on Wednesday. We'll have class in the beginning, but then in the last 40 minutes we'll have the assessment. Have a great day.